Thank you, and had I known you've been chasing me, I would have gone a lot slower. So I appreciate for the opportunity to be here, and frankly, I was a little shocked because I thought, why am I not part of this organization? So Rosemary, we will have to catch up. So I'm going to talk a little bit about Viridity Energy. I know you guys have been speaking about sustainability, and I caught a little bit of the DOE's remarks this morning, and really what we're talking about is basically how we're changing the landscape for electricity power and moving away from basically an industry that's dominated by central station power plants to one that involves central station power plants like coal, like nuclear, like gas, and then adds on to it distributed energy such as solar, wind, CHP, and load as creating a smart grid that involves all of these resources as a mechanism to create reliable, cost-effective, environmentally clean electric power for both the country and actually internationally. So let me see how this works. It must be this way. So we are, the company is Philadelphia-based, and our real focus is that we developed what we call a real-time decision tool. That's a software platform that we work with large energy users and middle-sized energy users with, that we actually communicate directly to your to building management systems, distributed energy resources, solar, etc., and also back to the grid. And what we do is we optimize the use of energy based on real-time prices in the wholesale market. And then what we're doing is using the ability to use distributed energy resources as well as load to get people to shift usage or curtail usage, and a mechanism that's based on real-time wholesale prices, and then sell that unused energy back into the grid as virtual power. So effectively what we're doing is we're taking these sometimes insurance policies, sometimes renewable assets, and buildings themselves and turning them into working energy assets that help people minimize their cost of electricity. But also over time, when we aggregate it, it actually minimizes the cost of price of electricity on the grid, and I'll talk a little bit about how that all works. My background, by the way, is I came from the electric utility, used to be the chief operating officer of PJM, which runs the power grid that represents about 20% of the load in the U.S. And so I'm coming from the perspective of how do we make the grid work better from a standpoint of efficiency, and knowing that that efficiency moves down to the customer location because it helps reduce prices for everybody. So start with basically my simple way of looking at the grid. The power grid itself is really a single machine. And because electricity is the only product known to mankind that is actually produced and consumed simultaneously, it means that everything we do on the grid, whether we're turning on a light or turning on a generator or turning off a light or turning off a computer, affects what's happening on the grid itself, because the grid has to remain in balance, meaning that power consumption and power production have to balance out at all times. And the way we work in the U.S., we actually have 3 power grids. One serves the eastern U.S. that goes essentially from the Rocky Mountains all the way to the ocean. One serves Texas. Texas is an electric island. And one serves the West Coast. And everything on that grid is interconnected. So that's why when we had trees falling on lines in Ohio back in 2003, we saw a massive blackout stretching all the way to New York, just cascading, because it's all real-time, moves at the faster speed of light. So what that means from that standpoint is that when power grid operators like PJM are trying to keep the grid in balance, they have 2 choices. When someone turns on a light, they have to either increase a generator output or they have to reduce consumption somewhere else, which means that the ability to reduce consumption on the grid has the same value as increasing production, because the only way the power grid works is if it stays in balance. And if we can reduce consumption based on price, what that does, it allows the grid to stay in balance. But what's most important is that the price of electricity, because it's real time, goes up as consumption increases. So demand, it's the law of economics, demand sets supply price. Demand goes up all the time. 15-minute interval, every second of the day. It goes up or down. So as demand goes up, for example, like yesterday when you have hot, humid weather, that means you're running more expensive generators. The way the price is set in the grid, it's set at that last kilowatt hour of production that's necessary to keep the grid in balance. And so when demand increases, price increases. When we can actually reduce demand based on price, what happens is that price reduces everywhere, and so customers get the benefit of a much more efficient price. And now when the grid, what happens, they also get paid. And that's what I'm going to be talking about today. So basically, what's going on is last year, the Federal Energy Regulatory Commission that regulates prices in the wholesale market issued a rulemaking, it was 2 years ago, that says that anybody who is able to reduce consumption based on price, the value of that reduced kilowatt, which we call a negawatt on the grid, it has the same value as a production of generation. So for example, 2 days ago, prices in this region went from, and I'm talking in the wholesale level, went from an average of $80 to $100 to $400 an hour. If somebody at that point said, hey, what I'm going to do is I'm going to shift my energy usage because I'm going to pre-cool my building and I'm going to reduce my demand during that hour and I'm going to sell that reduction back to the grid, they get paid that price by the grid operator. And so what's happening is, from the grid operator's perspective, they're looking at it and they're saying, I need people I could either reduce their generator output or reduce their demand, increase their generator output or reduce their demand. I'm indifferent. I just need to keep it in balance. If someone's willing to reduce their demand, I'll pay them the same amount. And so that's what's changing the world, because now we have a huge market for distributed energy resources that now can get compensated on the same basis as traditional generation in the markets, which is really where we need to go as an industry. So what's important for that is a couple things. One is that by you doing this is that you're creating an asset. So we work with some users who have, for example, solar and storage production facilities. They may be able to use ice storage, et cetera. What we're doing now is we're able to say to them, based on forecasted prices on the grid, tomorrow, this is how you should operate your system. And it gives them then the advantage of being able to operate more efficiently based on prices in the market, but then we monetize that back for them on the grid. So it's a difference between being reactive and actually being proactive in terms of how you manage your energy use and doing it in a way that helps you really reduce the effective cost of electricity, but turn these insurance policies into real assets. And let me slow down, because I know we're running a little bit behind. So in terms of all that, the way I look at it is there's the difference between what folks normally think of as demand response. I'm sure most of you are familiar with utility programs that allow for people to get either a reduced rate or a payment when they're willing to reduce their consumption based on a request by the local utility, or in the case of this region, sometimes the grid operator, PJM. In those instances, what's going on is that the grid is getting overheated, in the sense is that we're reaching peak demand. There's a concern that we're going to be running out of generation. And so when you have customers who are willing to voluntarily reduce during that time, they're replacing generation on the grid, and they get a payment for what we call demand response. That's sort of been going on since the 70s and 80s in the grid. And really what it is, it's a way of feeling the time is again, it's real time. There's not really storage available. When the grid gets stretched, we have to do what we can to avoid outages, et cetera. What we're talking about in terms of real-time demand response is something quite different. When you think about it, what I'm talking about is using the ability for people to voluntarily reduce load, such as send a shift home, turn on their backup generators, as really a safety net for the grid. Real-time demand response is actually quite different, and what it is, it's actually proactive in a sense. Is what we do is we look at prices in the market, we forecast what the price is going to be like tomorrow, and then we identify an opportunity for people to manage their energy use that's non-disruptive and turn back and really sell back what we call that virtual energy back into the grid. So where traditional demand response is reactive and utility controlled, proactive, what we call dynamic load control or demand control, is actually looking at it from the customer's perspective and saying, if I have this information and I know what prices are going to be and I can control my usage in a way that's non-disruptive, I'm going to try to be a more efficient user, and now I have an opportunity to monetize that back in the market and actually get paid for that behavior because I'm providing a service back into the power grid. So those are sort of the other elements. The importance of that, though, is that it's under your control. Secondly, it's for us is that with our software system, it goes from a manual to an automatic process. What we do is we actually work with customers. We help them identify what their preferences, what their constraints are. We give them the opportunities in the market, and then when those opportunities exist, we send a signal, a bias signal, to their building management systems or whatever other devices they want us to send them to. And then those devices respond and based on the signal so that they're responding back to real-time prices and they're not doing it in a way that's disruptive. So let me give you an example. Drexel University is one of our clients. We control about 80% of the campus. What Drexel does is they say at different price points, for example, when the price of power hits $120, they're willing to move their thermostats a degree or two from 74 maybe down to up to 75 or 72 up to 74 based on where prices are. What we'll do then is we have a network operations center that looks at the prices in the market. We forecast 10 days out. We say, well, tomorrow it looks like prices are going to be up in the $200 to $300 range. Drexel also has some ice-making equipment where they can make ice at night. We tell them when they should make ice, when they shouldn't make ice. Then we send a signal to their building management system and say, look, during the hours basically 2 to 4 p.m., looks like prices are going to be high. Why don't you pre-cool let's pre-cool the buildings between 10 to 2 so that during 2 to 4, instead of running your air conditioners full out, we'll back them off. That shows up as a load reduction on the grid, and during those high price hours, what you're doing is you're selling back, and you're shifting really your load so that you're consuming more during low price times and selling high. So buy low, sell high. That's what they're doing. So they're day trading. But what they're doing is that they're also taking the efficiency of their buildings. So for example, one of our favorite buildings at Drexel is the law library. Law libraries have tons of thermal mass. We can do a lot with that law library in terms of shifting when it's consuming and changing, and nobody feels a difference because the books themselves are retaining the cooling and heating. So what you're doing is you're making buildings very efficient. If you add into that, such as what we're doing with SEPTA, the train station, or another building where we're using backup generation and solar and storage, this becomes really then a system that everybody's working, all these assets are working together, and what happens then in the end, from the customer's perspective, is they're not buying when prices are high. In fact, they're selling, so they're saving more, and they're really optimizing their uses against prices in the grid. The other thing that we're doing is, and I think somebody mentioned this today, there are other products that they're available. For example, the grid needs to have resources that respond very, very quickly, like within 2 seconds. So we provide other services. For example, we're working with SEPTA that has a battery, and we're using the battery system to provide a regulation service back to the grid. So what's happening now is SEPTA is collecting energy from its trains, putting it into a battery, using the battery to store the energy so that it's available to SEPTA when the prices are higher, and also using the battery to provide grid support. So something that used to be a cost has now become an asset, and SEPTA stands to make somewhere between $500,000 to $750,000 a year off of an asset it needs to help secure the trains, but now it becomes a revenue source because it's tied back to the grid and is being used as a resource for the grid. The other pieces of what's very important is to think about the world is changing, and I know you folks are interested in renewable fuels. As we're looking at adding CHP